Let's say there's a rocket car moving in a circle, but it has the ability to shorten its tether. So shown in the picture here, we have a rocket car and there's like a little device here attached to it that's going to be able to reel in some of this tether. If the rocket car started out with a speed of 4 meters per second with a 6-meter long tether, but then reeled it into 3 meters, what is the resulting speed assuming conservation of angular momentum? By what factor did its kinetic energy increase? I think conservation of angular momentum makes sense here because in reeling in this tether, that's not going to really apply any torque. It's not going to like force the rocket car to rotate in any way. That torque or that force that is associated with the reeling in is really directed in the radial direction and is not at right angles to it, which is what it would need to be in order for there to be a torque. So that's why it makes sense what it's saying there, that we should assume conservation of angular momentum. And so I will write that here and say L initial is equal to L final. In this case, since we're just talking about a point-like object, it might make sense to use MRV for both the initial. I'm going to say it's MR initial, V initial is equal to MR final, V final, since the mass should be the same for both final and initial. But the tether is being shortened, which means the distance r that we're talking about, the radial distance r, is really the corresponding to the length of the tether. And it might make sense that the rocket car is going to speed up in order to conserve angular momentum. Let's see what happens. So we can say that v initial, I think, is equal to the given 4 meters per second. R initial is equal to the given 6 meters. R final is equal to 3 meters, so it's half of what it was, right? And V final is the thing that we're asking for. So if I isolate V final by dividing by both sides by R sub f, I could write that as an expression here as Ri over Rf multiplied by V sub I, and that would make sense because that would be 6 meters divided by 3 meters. The meters would cancel, so I'm not even going to write them, times the 4 meters per second. I predicted it would speed up, which might make sense that it would do that. And it's going to speed up by a factor of 2 because 6 over 3 is 2 times 4 is equal to 8 meters per second. Now, the second part of this question is by what factor did its kinetic energy increase? And it turns out for a rocket car like this, it's perfectly fine to use the formula 1/2 mv squared, even though it's rotating. So you could use the rotational kinetic energy formula and try to figure out the correct moment of inertia in that. For each case, it would complicate things a bit, but since it's just a point object moving with a speed v, it doesn't really matter that it's moving in a circle. 1/2 mv squared will give you the same answer and is far easier to do. And in this case, since the velocity or the speed increased from 4 meters per second to 8 meters per second, that represents a doubling of the speed. And for kinetic energy 1/2 mv squared, a doubling of speed results in a factor of 4 increase in the kinetic energy, which is remarkable. So I'm going to box my answers, right? Because the answer to the first question was that one, but the second one I kind of just talked my way towards. But it's remarkable in that if you ask, like, well, how did that happen? Right? If I increase the energy of a system, can that just happen by itself? Or did something have to do work? And the answer is something did do work. When this device was reeling in the tether, there was tension force here. It had to do work against that. So where this kinetic energy actually came from, that was supplied by whatever like power supply was powering this device that was reeling the rocket car in. Anyway, let's check those answers now. We can see it is 8 meters per second and that factor of 4.